Okay. Now, it's preferred that we not only know the value of this integral, we also need to know the value of ax squared dx. But this is almost immediate if you know this value, because you see this is the same thing as negative infinity to infinity of e to the negative square root of ax squared dx. And you're setting u as square root of ax, so that du would be square root of a times dx, so that dx is 1 over square root of a du. And that means you get integral from negative infinity to infinity of e to the negative u squared, and dx is 1 over square root of a du. With that u substitution, you can bring this in front and look at what integral you have. What's this value? Square root of pi. It's exactly the same as the first one, right? The same thing. Yeah. The only difference is here I have x, here I have u. It's the same integral, right? So we know that it's 1 over square root of a times square root of pi, which is equal to square root of pi over square root of a. So that's the answer to this one. So let me write over here e to the negative ax squared dx equal to square root of pi square root of a. Now, I want to show you some cool tricks that physicists like to use because when they do field theory or some really hard physics questions, they have to compute integrals like this, but with some polynomial in front. Okay, so let me first ask, what is that? Negative infinity to infinity of x times e to the negative ax squared. Oh, this is easy.
This is easy.
Yeah, this is easy, but it's easier than you think. What's the answer to this? I know why you said it's easy, because you can solve this by using u substitution, right? But you know the answer already. What is it? This is even or odd? This much.
Oh,
Even.
0?
Yeah, this is odd.
0.
Odd times even.
0.
So this, the graph of this will be like that, okay? And they cancel. So the next interesting thing would be this one, right? And this can be solved in the same way we obtained this one. You can go to polar coordinate system. There will be extra. This time it will be not r times e to the negative ar squared. It will be r cubed times e to the negative ar squared, and then another u substitution, but this time with the tabular integration will be needed. Integration by parts will be needed. So that will be one way to do it. A physicist, a very famous physicist named Feynman, who was a really good math student, and when he was an undergrad, he had a professor who would solve all kinds of really, really hard integration problems. And Feynman learned a trick from this professor, I forgot his name, and then later use that to get some of his results, and that became known as the Feynman trick. Okay? And what's the Feynman trick? The Feynman trick is to think of this and look at the left side as a function of a. Right? See, x is integrated away, but a is still there. So this left side, that integral depends on a. Do you agree? Right? And of course, this right side is a function of a as well, right? So the Feynman trick is to take this one and differentiate both sides by a, because it's a function of a. Let's see what that gives us. Okay, now mathematicians usually hate this, bringing derivatives inside. So there's some mathematical analysis part that I'm skipping, but let's say we can do that, okay? If we bring the dA inside, what happens here? What's the derivative of this? Just plain old chain rule, right? What is that? E to the negative ax squared times negative ax squared prime, where it's the derivative with respect to a, right?
Yeah.
If you differentiate a by a, what do you get?
So it's negative x.
1. It's like differentiate x, you get 1, right? If you differentiate x by x, you get 1. So if you differentiate a by a, that's 1, where we treat x squared as if it's a constant, okay? We're doing a partial derivative with respect to a. So this just becomes 1, and that's the result of the derivative of the inside function, right? Times dx on the left side, okay? On the right side, let's see what the derivative of square root of pi over square root of a is. Well, I don't know how to differentiate this, so let me try to rewrite this as a to the what power? Negative 1/2. Negative because it's in the denominator. Square root converts to 1/2 power, right? So you differentiate this. And now you can just use the power rule. Negative 1/2 comes front. And then you subtract 1 off. What's that? Negative 3 over 2. Right? Now this is equal to that. And isn't this almost what we want? What's the only difference? We want this, right? What's the only difference?
Negative sign.
There's a negative sign. So if we set these two equal and divide both sides by negative, here's what we get. We get this equals to positive 1/2 square root of pi a to the negative 3 over 2. Okay? And that's 10 times easier than having to go through the polar coordinates and doing all that all over again. Okay? That's called the Feynman trick. Okay? Yeah. Differentiating by something that looks like a constant. And this one you can further rewrite if you want. You can further rewrite it as square root of pi times 2a square root of a. Now, question. Then if I had x to the 4th, what would I do? How would I get the one with x to the 4th?
Differentiate twice.
Differentiate twice. Then you get the one with x to the 4th. If you want x to the 6th, differentiate it yet again. You just keep differentiating both sides. You get all the results of the even ones. The odd ones are always 0, so we don't care. Okay? So that's how you get all the polynomial times the Gaussian function. Yeah, so I'm going to show you another nice Feynman trick integration because we need it later. But then let me just conclude this section with another important one, which is integral from negative infinity to infinity of e to the negative ax squared plus bx dx. Okay, so if you have another bx there, what can you do? Well, you can do completing the square. You factor the negative a out so that you get x squared minus b over ax. Okay. And if you have x squared plus something x, what do you put at the end to make it a perfect square? Huh?
B squared.
4a squared?
Yeah, you take the half of the middle term and you square that, right?
Yeah.
So negative a x squared minus b over ax. Taking half of that is like b over 2a. And you take the square of that thing and add and subtract. Okay. Then this much here will be a perfect square. So it's negative a x minus b over 2a squared. Okay, so this much became this. But then the other one, negative a times negative b squared over 4a squared would be plus b squared over 4a. Okay? So with this, we now have the integral negative infinity to infinity of e to the negative a x minus b over 2a squared plus b squared over 4a. But b squared over 4a is just a constant, right? And if you have two things, you have e to the a plus e to the b, e to the a plus b, then that's same as e to the a times e to the b. So this, since that's a constant, we can bring it outside the integral. What that gives us is, it gives us e to the b squared over 4a.
Is it supposed to be squared?
Which one?
A.
No, this a canceled this a squared, so you
okay.
just have only a in the denominator, okay? All right, times integral from negative infinity to infinity of e to the negative a x minus b over 2a squared dx. Okay. Now, if you think about what this is just x shifted right by b over 2a. That's what it is, right? But since the interval is from negative infinity to infinity, even if you shift the graph this way, the area under the curve will be nonetheless the same. So this interval will be same as that. If you don't like that argument, we can just prove that using u substitution. You can say u is x minus b over 2a. Then du is what? Differentiating this gives you?
Yes.
Just 1, so du is just dx. So you can rewrite this one as integral from, well, even if you have infinity and negative infinity for x, subtracting any number still gives you infinity minus some number is infinity. Negative infinity minus some number is still infinity. So these bounds don't change. Normally you do have to change the boundaries, right? But these don't change, and you get e to the negative a u squared du. And now you see that this is exactly the same form as this form. So that's going to be e to the b squared over 4a square root of pi over square root of a.